Look up on a clear, moonless night, away from city lights, and you will see it. A faint, milky band stretching across the sky. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. We call it the Milky Way, but this band of light is not a road or a river. It is our home, seen from the inside, a spiral galaxy 100,000 light years across, containing over 200 billion stars. Within this vast island exist places so extreme they challenge our understanding. Black holes that anchor galaxies, stars moving at speeds that bend time itself, giants that dwarf our entire solar system. Our journey takes us from the galactic center outward, through the extremes of stellar life and death. By the end, you will understand how these cosmic phenomena connect to us, because every atom in your body was forged inside stars like these. At the heart of our galaxy, 26,000 light years from Earth, sits an object so massive and so dense that it bends the fabric of space and time into a funnel from which nothing can escape. Not matter, not light, not information of any kind. This is Sagittarius A star, the supermassive black hole that anchors the Milky Way, and it contains more mass than 4 million suns compressed into a sphere roughly the size of Mercury's orbit around our Sun. The environment near Sagittarius A star is violent. Gas and dust from dying stars fall toward the black hole, pulled by its immense gravity. This material cannot fall straight in because it carries angular momentum, a measure of its rotation and motion. To cross the event horizon, this momentum must be shed. So the doomed matter spirals inward, forming an accretion disk, a flattened, swirling structure where gas orbits at a significant fraction of the speed of light. At these velocities, friction between particles generates tremendous heat. Temperatures in the inner accretion disk reach 10 million degrees Celsius. At such temperatures, atoms are stripped of their electrons. The gas becomes plasma, a superheated soup of charged particles that glows intensely in X-rays and radio waves. This is what we actually detect when we observe Sagittarius A star. Not the black hole itself, which emits nothing, but the brilliant ring of material circling the abyss, radiating its final burst of energy before disappearing forever beyond the event horizon. Consider what it would be like to be near the event horizon. If you could somehow survive the crushing tidal forces and radiation hovering just above the boundary, you would experience time passing normally. Your heartbeat would feel normal, but if you looked outward at the rest of the universe, you would see time appear to speed up. Days would pass in minutes. Meanwhile, anyone watching you from a safe distance would see you moving in extreme slow motion, appearing frozen at the edge of oblivion. This is the nature of a black hole. It is not merely an object. It is a boundary in space-time, a place where the concepts of inside and outside, before and after, cease to have their ordinary meanings. The event horizon marks the limit of what we can know about the universe. Beyond it, causality breaks down. Information cannot escape. The laws of physics, as we understand them, may not apply. To understand the scale of this object, imagine taking 4 million suns and crushing them together until they fit into a space you could cross in a fast spacecraft in about 3 months. That is the event horizon of Sagittarius A star, the boundary beyond which physics as we know it breaks down completely. The entire mass of 4 million stars, packed into a region of space that, on cosmic scales, is incredibly tiny. The discovery of this object reads like detective work conducted across decades. In 1933, an engineer named Carl Jansky detected a faint radio hiss coming from the direction of Sagittarius while investigating static that interfered with phone calls. By the 1970s, improved radio telescopes revealed an extremely bright, compact source at the galactic center. Astronomers named it Sagittarius A star, the asterisk denoting something exciting. But what was it? The answer came from watching stars. Close to the galactic center, a handful of stars follow wildly eccentric orbits around an invisible point, whipping through space at velocities that defy explanation unless something incredibly massive is pulling on them. One star, S2, orbits this invisible object every 16 years, reaching speeds of 5,000 kilometers per second at its closest approach. By tracking S2's motion using Johannes Kepler's laws, astronomers calculated the mass at the center, 4.3 million times that of the Sun. There is only one thing in the known universe that can pack that much mass into such a small, invisible space. A black hole. But a black hole is more than just a massive object. It is a place where the rules of physics fundamentally change, where space and time themselves become so warped that they cease to function as separate entities. To understand this, consider what happens as you approach the event horizon. Imagine you could watch a clock fall toward Sagittarius A star. As the clock gets closer to the event horizon, something strange happens. The clock begins to tick more slowly, not because anything is wrong with it, but because time itself is running slower in the intense gravitational field. This is gravitational time dilation, predicted by Einstein's general theory of relativity. The closer the clock gets to the horizon, the slower it ticks. At the event horizon itself, from the perspective of someone watching from a safe distance, the clock would appear to stop completely. Time, as experienced by an outside observer, ceases to flow at the boundary of a black hole. But here is where it gets truly strange. From the perspective of someone falling with the clock, nothing unusual happens at all. Time continues to pass normally. You would fall through the event horizon in a matter of seconds or minutes, depending on the size of the black hole. You would not notice the moment you cross the boundary. There would be no wall, no barrier, no sensation of passing through anything. The event horizon is not a physical surface. It is simply the mathematical boundary beyond which escape becomes impossible, where the required escape velocity exceeds the speed of light. This creates a paradox of sorts. To an outside observer, you never quite reach the event horizon. You appear to slow down, freeze, and fade from view as your light becomes infinitely redshifted and dim. But from your own perspective, you fall straight through in finite time. Both perspectives are correct. This is one of the profound implications of relativity. There is no universal now. Time is relative, and near a black hole, this relativity becomes extreme. Yet by black hole standards, Sagittarius A star is remarkably quiet. The supermassive black holes at the centers of some galaxies consume vast amounts of material, blazing with the light of billions of suns. These active galactic nuclei are visible across billions of light years. Sagittarius A star, by contrast, is nearly dormant. It accretes material slowly, swallowing roughly the mass of Earth every few years. This makes it faint enough that only recently did technology advance to the point where astronomers could image it directly. In April of 2017, 8 radio telescopes scattered across the planet turned their attention to the galactic center. Working in perfect synchronization, these telescopes functioned as a single instrument with an effective diameter equal to that of Earth itself. The technique is called Very Long Baseline Interferometry, and it allowed astronomers to achieve the resolution necessary to image something the apparent size of an orange sitting on the moon. After years of data processing, the Event Horizon Telescope collaboration released the first image of Sagittarius A star on May 12, 2022. The image shows exactly what Einstein's equations predicted. A glowing ring of light surrounds a dark circular shadow. This is the photon ring, light from the accretion disk that has been bent and magnified by the black hole's gravity. The ring measures about 52 micro-arcseconds across, as seen from Earth. Translated to physical size, this means the bright ring has a diameter of 51.8 million kilometers. The shadow at the center is larger than the event horizon itself, about 5 times wider. This is the region where the gravitational field is so strong that light, if aimed even slightly wrong, curves back toward the black hole and never escapes. What you are seeing in that image is the silhouette of space-time itself, warped beyond recognition. The image reveals something subtle but important. The ring is not perfectly symmetrical. One side appears brighter than the other. This is Doppler beaming, caused by material in the accretion disk moving toward us at relativistic speeds on one side and away from us on the other. Light from the approaching side is compressed and intensified, while light from the receding side is stretched and dimmed. This asymmetry tells us the disk is rotating and reveals the direction of that rotation. It also tells us something profound. The matter in this disk is moving so fast that the ordinary rules of motion break down. At these speeds, time, distance, and mass all behave differently than they do in our everyday experience. And yet, for all its strangeness, Sagittarius A star is not an anomaly. Nearly every large galaxy has a supermassive black hole at its center. The relationship between the mass of these black holes and the properties of their host galaxies suggests they play a crucial role in galactic evolution. They regulate star formation. They redistribute energy. They shape the structure of the galaxies they inhabit. Sagittarius A star is not a parasite or a destructive force. It is the gravitational engine that has shaped the Milky Way for billions of years. Our Sun, located 26,000 light-years from Sagittarius A star, orbits this black hole once every 250 million years. Every star you see in the night sky is caught in the same slow rotation around the galactic center. Every nebula, every cluster, every wandering comet. The Milky Way is not a static collection of stars, but a dynamic system held together by the invisible hand of gravity emanating from this 4 million solar mass anchor at its core. But Sagittarius A star is more than just massive and distant. It is surrounded by one of the most extreme environments in our galaxy. Orbiting near the event horizon are stars that move faster than almost anything else in the Milky Way, stars caught in a gravitational dance so intense that the fabric of space-time itself becomes stretched and distorted. Among them is a star that skims the black hole at 8% of the speed of light, a velocity so extreme that relativistic effects become visible. Time slows down for this star. Its mass increases. The distances it travels contract. That star will be our next stop. There is a star that moves so fast it could cross the entire United States in 1/5 of a second. It could travel from Earth to the Moon in 16 seconds. At its peak velocity, it reaches 8% of the speed of light. This is S4714, the fastest known star in the Milky Way, and it achieves this impossible speed through a dance with death, skimming so close to Sagittarius A star that the black hole's gravity accelerates it to velocities where the normal rules of physics break down. To understand how extraordinary this speed is, consider that the Parker Solar Probe, humanity's fastest spacecraft, travels at just over 100 kilometers per second when it swoops closest to the Sun. S4714 moves more than 200 times faster. At 8% light speed, relativistic effects become visible. Time itself begins to behave strangely. The star's mass increases. Distances contract in the direction of motion. S4714 exists in a realm where Einstein's theories stop being abstract mathematics and become physical reality. The star follows what astronomers call a highly eccentric orbit. Picture an extremely stretched oval, so elongated that one end nearly touches the black hole, while the other swings out into the relative emptiness of the galactic center. S4714 has an orbital eccentricity of 0.985, about as elongated as a stable orbit can be without the star simply escaping into space, on a scale where 0 represents a perfect circle, and 1 represents escape velocity. S4714 dances on the edge. At its closest approach, called periapse, S4714 passes closer to the black hole than Saturn orbits our Sun. The star is practically grazing a supermassive black hole, coming within about 12 astronomical units of the event horizon. The orbit takes 12 years to complete. For most of that time, S4714 moves through the outer regions of the galactic center at relatively sedate speeds. But as it begins its inward plunge, gravity takes hold. The star accelerates, faster and faster. The black hole's immense mass pulls it forward with crushing force. By the time S4714 reaches periapse, it is moving at more than 8% of light speed, or 15,000 miles per second, blazing past the event horizon in what must be a terrifying cosmic blur before swinging back out into the void. What would it be like to be on a planet orbiting this star? The view would be staggering, though you would not survive long enough to appreciate it. For most of the 12-year orbit, Sagittarius A star would appear as a dark sphere surrounded by a glowing accretion disk, slowly growing larger as your system approached. The sky would be crowded with other S-stars, those dozens of massive stars locked in similarly extreme orbits, their paths crisscrossing through the galactic center like fireflies dancing around a flame. As your system plunged inward, the black hole would grow from a dot to a disk to a vast, dark circle that consumed half the sky. The accretion disk would blaze with impossible brightness, pumping out X-rays that would sterilize any world unfortunate enough to be caught in this environment. The tidal forces would become extreme. Just as Earth's oceans bulge toward the moon in response to its gravity, S4714 itself would be stretched and squeezed by the black hole's grip. The side of the star facing Sagittarius A star would experience far stronger gravitational pull than the far side, attempting to tear the star apart. This squeezing and stretching has a name. Astronomers call stars in these extreme orbits squeezars, objects that get so close to a black hole they are squeezed by its tidal forces. The theory, proposed by astrophysicists Tal Alexander and Mark Morris, suggests these stars have their orbital energy converted into heat through tidal interactions, making them shine brighter than they should. At each pass, the tidal forces convert a fraction of the star's close orbital energy into heat, making the star shine more brightly than it normally would, and contributing to the star's orbital decay. S4714 may be one of the first confirmed squeezars, a star literally being cooked by the gravitational forces trying to rip it apart. But there is something even stranger happening. At 8% of the speed of light, time dilation becomes measurable. Time runs at different rates depending on velocity and gravity. For S4714 during its high-speed periapse, time passes slightly slower than for distant observers. The star is, in a very real sense, traveling into everyone else's future. If you could place synchronized clocks at different points along S4714's orbit, they would tick at different rates. The existence of S4714 raises profound questions. How did a star end up in such an extreme orbit? Stars cannot form so easily near a black hole, so S4714 must have moved inward, perhaps by approaching other stars and objects in the S cluster, which caused its orbit to shrink significantly. The galactic center is a violent place, crowded with massive stars, whose gravitational interactions can fling smaller objects into wild trajectories. S4714 was likely once in a more distant, more stable orbit, before a series of gravitational encounters nudged it inward, each interaction tightening the spiral until the star found itself on this suicide run. The star will not last forever in this configuration. The tidal heating from its close passes around Sagittarius A star causes the star to lose energy. Each orbit brings it slightly closer to the black hole. Eventually, perhaps in a few million years, S4714 will cross the tidal disruption radius, the point where the black hole's gravity becomes stronger than the star's own gravity, holding it together. When that happens, S4714 will be torn apart in a process called spaghettification. The star will be stretched into a long stream of plasma that spirals into the black hole, briefly flaring in X-rays before disappearing forever beyond the event horizon. But for now, S4714 endures. Every 12 years, it completes another lap, accelerating to impossible speeds, skimming the edge of oblivion, and swinging back out into the relative safety of the outer galactic center. It is a cosmic speedster, a star caught in circumstances so extreme that it bends the fabric of space-time itself. S4714 represents one extreme of stellar existence, velocity. But our next wonder showcases a different kind of extreme. If S4714 is about speed, the next star is about size. Not just large, but incomprehensibly vast. A star so enormous that if you placed it where our sun sits, its surface would extend beyond the orbit of Jupiter. A red supergiant so immense that it challenges our understanding of what a star can be. That giant awaits us next. There is a star so large that if you replaced our sun with it, its surface would stretch past the orbit of Mars and possibly reach as far as Jupiter. A star with a radius estimated at 909 times that of the Sun, containing a volume so vast that 750 million suns could fit inside it. This is UY Scuti, one of the largest known stars in the Milky Way, a red supergiant so immense that it challenges our ability to comprehend physical scale. To grasp the size of UY Scuti, start with something familiar. The Sun is enormous by human standards. Its diameter is 109 times that of Earth. You could fit more than 1 million Earths inside the Sun. But UY Scuti makes our Sun look like a grain of sand beside a beach ball. If Earth were the size of a marble, the Sun would be the size of a large beach ball about 3 feet across. UY Scuti, at that same scale, would be a sphere nearly 4 miles in diameter. That is the scale we are dealing with. A star so large that light itself, traveling at 300,000 kilometers per second, takes 7 hours to cross from one side to the other. The star sits roughly 5,900 light-years from Earth in the constellation Scutum, the Shield. At that distance, it appears as a faint reddish point of light, too dim to see with the naked eye. Its brightness varies over time, pulsating with a period of about 740 days, swelling and contracting like a slow cosmic heartbeat. This pulsation is one of the defining characteristics of red supergiants. The star is not stable. Its outer layers expand and fall, driven by the violent processes occurring deep in its core. UY Scuti glows with a surface temperature of approximately 3,500 Kelvin, cool by stellar standards. Our Sun's surface sits at 5,770 Kelvin. This cooler temperature gives UY Scuti its distinctive red color, but do not mistake cool for dim. UY Scuti is about 124,000 times more luminous than the Sun. If you could somehow place UY Scuti at the same distance from Earth as our Sun, currently about 150 million kilometers, the heat would vaporize our planet instantly. The sheer energy output of this star is staggering. How does something become this enormous? The answer lies in the life cycle of massive stars. UY Scuti was not always a giant. It began as a main sequence star, perhaps 10 to 20 times more massive than the Sun, burning hydrogen in its core through nuclear fusion. For millions of years, it sat in equilibrium, the outward pressure of fusion balancing the inward pull of gravity. But fusion changes a star's internal composition. Hydrogen fuses into helium, and over time, the core becomes enriched with helium ash. Eventually, the hydrogen in the core runs out. When that happens, fusion stops. Without the outward pressure from fusion, the core begins to collapse under its own weight. As it collapses, it heats up. The temperature rises until the shell of hydrogen surrounding the core becomes hot enough to ignite. Hydrogen shell burning begins, and this releases enormous amounts of energy. But that energy does not make the star smaller. Instead, it makes the outer layers expand. This is the paradox of red giant evolution. The core is contracting and heating up, but the outer envelope is expanding and cooling down. The envelope expands to several hundred times beyond the former size of the star, and the energy at the star's surface becomes far more dissipated, causing the bloated surface to cool and turn from white or yellow to red. UY Scuti has entered this phase. Its core is dense and hot, likely fusing helium into carbon and oxygen, but its outer layers have swollen to nearly 1 billion kilometers in diameter. The internal structure of UY Scuti is layered like an onion. At the very center sits a core where helium fuses into carbon and oxygen through a process called the triple alpha process. 3 helium nuclei, each called an alpha particle by nuclear physicists, combine to form a single carbon nucleus. Sometimes the process overshoots and produces oxygen instead. This is where the carbon and oxygen in your body came from. They were manufactured inside stars like UY Scuti. Surrounding the core is a shell where hydrogen continues to fuse into helium. Above that lies a vast envelope of cooler gas, the extended atmosphere that gives UY Scuti its enormous size. Red supergiants develop deep convection zones reaching from the surface over halfway to the core, and these cause strong enrichment of nitrogen at the surface. Material from deep within the star is dredged up to the surface through convection, bringing fusion products from the interior out into the visible layers. The star is constantly mixing itself, churning like a pot of boiling water on a cosmic scale. This size comes with instability. The outer layers of UY Scuti are only loosely bound to the star. The gravitational pull at the surface is weak compared to the radiation pressure pushing outward from the core. Red supergiants are observed to rotate slowly or very slowly, likely braked by mass loss. The star is shedding material into space, losing mass through a stellar wind. Over time, this wind strips away the outer layers, exposing the hotter interior and changing the star's appearance. The pulsations add another layer of complexity. Every 740 days or so, UY Scuti swells and then contracts. During expansion, the surface cools and dims. During contraction, it heats up and brightens. These are not small changes. The star's radius can vary by tens of millions of kilometers over the course of a pulsation cycle. The mechanism driving these pulsations involves the opacity of the star's outer layers. As the layers heat up, they become more opaque, trapping energy. This causes them to expand. As they expand, they cool and become more transparent, allowing energy to escape. This causes them to contract. The cycle repeats endlessly, a natural oscillation built into the structure of the star. What would it be like to observe UY Scuti up close? Imagine approaching the star from a distance. At first, it would appear as a bright red disk, growing larger as you got closer. But unlike the Sun, which has a relatively sharp edge, UY Scuti's boundary is diffuse. Stars have diffuse edges. The density of the outer atmosphere gradually decreases until it merges with the surrounding space. There is no clear surface, just a gradual transition from the opaque layers where light is generated to the transparent regions where it escapes. As you descended into the outer layers, you would find yourself surrounded by a thin, hot gas. The density here is lower than the best vacuum we can create in laboratories on Earth. And yet, because of the star's immense size, there is so much gas that it becomes opaque. Light generated in the deeper layers struggles to escape, scattered and absorbed countless times before finally breaking free into space. If you could somehow survive the heat and descend deeper, the temperature and density would increase. You would pass through convection cells, vast rising plumes of hot gas, and sinking rivers of cooler material. Each cell might be larger than the entire Earth. The star is a churning, roiling mass of plasma, driven by the enormous energy output from the fusion reactions deep in the core. UY Scuti is old by stellar standards, perhaps 10 to 20 million years since it first formed. This might sound like a lot, but our Sun is 4.6 billion years old. Massive stars like UY Scuti burn through their fuel much faster than smaller stars. The more massive a star, the hotter its core must be to support the weight of the overlying layers. Higher temperatures mean faster fusion, which means a shorter lifespan. UY Scuti burns through its fuel so quickly that the star is likely ending its life cycle and may only have a few million years left. The end will not be quiet. When the star exhausts its nuclear fuel and produces an iron core, the core will collapse in less than a second. The star will explode as a supernova, briefly outshining entire galaxies. When UY Scuti explodes, it will be visible from Earth in broad daylight at 5,900 light-years away. The blast will eject the star's outer layers into space at tens of thousands of kilometers per second, enriching the surrounding interstellar medium with heavy elements forged in the explosion. But UY Scuti is not alone in its final journey. Across the galaxy, massive stars are ending their lives in similar ways. Some explode as supernovae, others collapse directly into black holes, and in certain regions of the Milky Way, these dying stars cluster together, creating environments of astonishing beauty and violence. Places where hundreds of massive stars crowd into a space just a few light years across, all racing toward their explosive ends. One such place awaits us next, a stellar city unlike anything else in our galaxy, a cluster so dense and so energetic that it will produce more than 1,500 supernovae in the span of just a few million years. There is a star system so luminous that it shines with the light of 5 million suns, so massive that it contains more than 100 times the mass of our own star, so unstable that in the mid-1800s it nearly tore itself apart in an explosion that briefly made it the second brightest star in Earth's night sky. This is Eta Carinae, a hypergiant binary system 7,500 light-years away in the southern constellation Carina, and it is one of the most likely candidates to become the next visible supernova in our galaxy. The sheer scale of Eta Carinae defies easy comprehension. The primary star in this system radiates 5 million times more energy than our Sun. If you could replace the Sun with Eta Carinae's primary, the heat would vaporize Earth instantly, and Mercury and Venus. Even Mars, sitting 140 million miles away, would be scorched beyond recognition. The star's luminosity is so extreme that it sits dangerously close to the theoretical limit for stellar stability. Above a certain brightness, a star's own radiation pressure can overpower gravity and blow the star apart. Eta Carinae dances on this edge. The system consists of two massive stars, locked in a tight orbit. The primary is a luminous blue variable, an extremely rare type of star that undergoes violent instabilities. These stars are among the most massive objects that can exist. The secondary star, itself 30 to 80 times the mass of the Sun, orbits the primary every 5.54 years in a highly eccentric path. When the two stars approach each other at their closest point, their powerful stellar winds collide, creating shock waves that heat gas to millions of degrees and generate intense X-ray radiation. But what truly sets Eta Carinae apart is what happened in 1843. For several years leading up to that date, the star had been brightening. Observers in the southern hemisphere watched as it climbed from 4th magnitude to 2nd, then to 1st. In April of 1843, Eta Carinae reached its peak. For 3 days, from March 11th to 14th, it outshone every star in the sky except Sirius, blazing at magnitude -1. At peak brightness, the luminosity reached 50 million times that of the Sun, releasing as much visible light as a genuine supernova explosion. And yet, the star survived. This event, now called the Great Eruption, remains one of the most puzzling phenomena in stellar astronomy. Eta Carinae did not explode. It did not collapse. Instead, it ejected a massive shell of material into space, between 10 and 40 times the mass of the Sun, hurled outward at speeds reaching 650 kilometers per second. That is nearly 1.5 million miles per hour. The star shed this enormous amount of mass in just a few years, and somehow remained intact. The ejected material did not expand uniformly in all directions. Instead, it formed a bizarre hourglass shape, two massive lobes extending outward from the star's poles with a dense equatorial disk connecting them. This structure is called the Homunculus Nebula, from the Latin word for little man, though there is nothing little about it. The nebula is now about a light-year long and continues to expand at more than 1.3 million miles per hour. Standing at the center of this nebula, you would see towering walls of glowing gas, receding in opposite directions, expanding so fast that their motion would be visible over the course of a human lifetime. The homunculus is not smooth or symmetric. Recent, detailed observations reveal trenches near the poles of each lobe, positioned point-symmetrically from the center. There are protrusions extending from the equatorial region, holes near the center of each polar lobe. The structure is complex, sculpted by the interaction of the binary stars and their colliding stellar winds. The shape itself provides evidence that the Great Eruption was influenced by the binary nature of the system, though exactly how remains a subject of intense research. Why did Eta Carinae erupt in 1843? No one knows for certain. The most popular hypothesis proposes that the star's luminosity became so great that radiation pressure overpowered the gravity holding the star together. But this explanation is incomplete. Some astronomers suggest that the companion star may have played a role, perhaps transferring mass or triggering instabilities during one of its close approaches. The peaks in Eta Carinae's brightness in the decades before the Great Eruption coincided with periastron, the point where the two stars come closest together, hinting at a connection between the binary orbit and the outburst. After the Great Eruption, Eta Carinae faded. By 1868, it had become invisible to the naked eye. It remained dim for decades, hovering around 8th magnitude. Then, in 1890, it flared again in a smaller eruption, reaching 6th magnitude before fading once more. This smaller event produced what astronomers call the Little Homunculus Nebula, a much tinier structure with only about 1/10 of a solar mass. Since the mid-20th century, Eta Carinae has been brightening again. It reached 4th magnitude by 2014, making it once more visible without optical aid for observers in the southern hemisphere. The star's behavior is erratic, unpredictable. Its brightness varies over timescales ranging from months to years. Every 5.54 years, when the secondary star passes through periastron, there is a sudden drop in X-ray emission as the two stars' winds interact differently. The system dims briefly in visible light, then recovers. The environment near Eta Carinae is extraordinarily violent. The primary star loses mass at one of the highest rates known, approximately 1,000th of a solar mass per year. This means that every 1,000 years, the star sheds the equivalent of an entire sun into space through its stellar wind. The wind is entirely opaque, appearing as what astronomers call a pseudo-photosphere, a shell of material so dense that it hides any true physical surface the star might have. The wind moves at about 420 kilometers per second, though some material reaches velocities as high as 3,200 kilometers per second. The secondary star also drives a powerful wind, probably moving at around 3,000 kilometers per second, typical for a hot O-class star. Where these two winds meet, they collide in a standing shock wave that heats gas to 10 million Kelvin and produces copious X-rays. The collision region forms a cavity between the two stars, a zone where the winds are compressed and deflected. This cavity plays a role in shaping the homunculus and continues to influence the structure of material being ejected even today. What would it be like to view Eta Carinae from nearby? From a safe distance, say 10 light-years away, the star would appear as a brilliant blue-white beacon, far brighter than Venus appears from Earth. The Homunculus Nebula would stretch across a significant portion of the sky, a glowing hourglass structure with intricate detail visible in even modest telescopes. The nebula would show variations in color, from the reddish glow of dust heated by the central stars to the bluish reflection of starlight scattered by gas. But nothing about Eta Carinae is stable. The system is not in equilibrium. It is dying. The primary star has already lost at least 30 solar masses. Eventually, the core will fuse heavier elements until it produces iron. Once an iron core forms, the star's fate is sealed. The core will collapse in a fraction of a second, rebounding in a catastrophic supernova explosion. Given Eta Carinae's mass, the explosion will be spectacular. It may even be a hypernova, an especially energetic variety of supernova that could produce a burst of gamma rays visible across vast distances. When it explodes, Eta Carinae will briefly outshine the entire Milky Way. From Earth, 7,500 light-years away, the supernova will be visible in daylight. It will cast shadows at night. It will be far brighter than any supernova observed in recorded human history, except for possibly the supernova of 1054, which produced the Crab Nebula and was visible during the day for 23 days. The explosion will not happen uniformly. The binary companion, if it survives the blast, will be flung into space at high velocity, perhaps becoming a hypervelocity star like S4714. The Homunculus Nebula will be hit by a shock wave moving at tens of thousands of kilometers per second. heating it, compressing it, and likely destroying much of its structure. The surrounding Carina Nebula will be flooded with radiation and high-energy particles. Any planets or young stars within a few tens of light years will be subjected to intense bursts of X-rays and gamma rays. And the material ejected by the supernova, enriched with heavy elements forged in the explosion, will mix with the interstellar medium and eventually be incorporated into new stars and planets. The carbon in future life forms, the oxygen in their atmospheres, the silicon in their rocks, all will carry the signature of Eta Carinae's violent death. When will this happen? No one knows. It may be next year. It may be 1 million years from now. In astronomical terms, this is imminent. Eta Carinae is one of the closest supernova candidates to Earth. Astronomers watch it closely, monitoring its every fluctuation, hoping to catch the first signs of the final collapse. The Great Eruption of 1843 may have been a preview, a warning that the star is nearing its end, or it may have been an isolated event, unrelated to the eventual supernova. We cannot know, but we do know this: Eta Carinae is not stable. It is a ticking bomb in the southern sky, a star so massive and so luminous that its own energy is tearing it apart. It has survived at least one near-death experience. It will not survive the next. Eta Carinae represents the extremes of stellar violence and instability. But our next wonder takes us in a different direction, from death to birth. From a star on the edge of destruction to a region where new stars are being born at this very moment. A nebula so vast and so active that it is one of the most spectacular stellar nurseries in the entire Milky Way, a place where the interplay of creation and destruction shapes the future of our galaxy. That Cosmic Foundry awaits us next. There is a place in our galaxy where stars are being born at this very moment, a vast cloud of gas and dust spanning about 300 light-years in diameter, large enough that light takes 3 centuries to cross from one side to the other. This nebula is one of the largest star-forming regions in the Milky Way, containing roughly 900,000 times the mass of our Sun worth of material, waiting to collapse, ignite, and shine. This is the Carina Nebula, a cosmic foundry where the raw ingredients of space are being transformed into new suns, new planets, new worlds. If the Milky Way were a city, the Carina Nebula would be its most active construction site. The fireworks started 3 million years ago, when the nebula's first generation of newborn stars condensed and ignited in the middle of a huge cloud of cold molecular hydrogen. Those stars, now massive and hot, pump enormous amounts of ultraviolet radiation and stellar wind into their surroundings, carving bubbles and cavities in the gas. But this destruction is also creation. The radiation compresses nearby clouds, triggering new waves of star formation. The process feeds on itself. Old stars sculpt the nebula. New stars are born in the compressed material. Those new stars grow up and begin sculpting the nebula themselves. The cycle continues. The nebula sits 7,600 light-years from Earth in the southern constellation Carina. From the southern hemisphere, it appears as a glowing patch in the night sky, visible even to the naked eye as a faint smudge along the Milky Way. Through binoculars or a small telescope, it resolves into a spectacular structure of bright emission nebulae, interspersed with dark lanes of dust. But to truly appreciate the Carina Nebula, You need to see it through the eyes of space telescopes that can pierce the dust and reveal what lies hidden within. In 2022, the James Webb Space Telescope turned its infrared cameras toward a region of the Carina Nebula known as NGC 3324. The resulting image, nicknamed the Cosmic Cliffs, became one of Webb's most iconic early photographs. The region is actually the edge of a gigantic gaseous cavity within NGC 3324, roughly 7,600 light-years away. The cavernous area has been carved from the nebula by the intense ultraviolet radiation and stellar winds from extremely massive, hot, young stars located in the center of the bubble. The image shows what appears to be a mountain range under a starry sky, peaks and valleys carved in gold and orange, glowing against the darkness of space. But this is not rock. The tallest of these mountains of gas and dust are 7 light-years high. 7 light-years. To put that in perspective, the nearest star to our Sun, Proxima Centauri, sits just over 4 light-years away. These pillars of gas and dust tower higher than the distance to the nearest star system. They are mountains in the truest sense, just not made of stone. They are structures of hydrogen, helium, and trace amounts of heavier elements, held together by gravity and shaped by radiation. The steam that appears to rise from the celestial mountains is actually hot, ionized gas and hot dust streaming away from the nebula due to intense ultraviolet radiation. The massive young stars above the cosmic cliffs are literally evaporating the gas, boiling it off into space. Dramatic pillars rise above the glowing wall of gas, resisting the blistering ultraviolet radiation from the young stars. These pillars survive because they are denser than the surrounding material. The radiation erodes their surfaces, but their cores remain intact, at least for now. Deep within these pillars, hidden from visible light telescopes, stars are forming. This period of very early star formation is difficult to capture because, for an individual star, it lasts only about 50,000 to 100,000 years. In cosmic terms, this is a blink. Our Sun has existed for 4.6 billion years. The brief period when it was still forming, when it was pulling itself together from a collapsing cloud of gas, represents less than 1/10,000th of its current age. Webb's infrared vision catches stars in this fleeting phase, revealing hundreds of protostars that would be completely invisible to optical telescopes. Protostellar jets and outflows, which appear in gold, shoot from dust-enshrouded, nascent stars. These jets are material being expelled from the poles of young stars as they accrete mass from their surrounding disks. The jets punch through the nebula at hundreds of kilometers per second, creating shock waves that light up in infrared. They are the birth cries of new suns, announcing their presence to the galaxy. The Carina Nebula is not a single uniform cloud. It is a complex of smaller nebulae, star clusters, and individual massive stars, all interacting in a chaotic but beautiful cosmic ecology. At its heart lies Eta Carinae, the doomed hypergiant we encountered in the previous chapter, surrounded by its homunculus nebula. Nearby sits the Keyhole Nebula, a dark cloud silhouetted against brighter emission. Multiple open star clusters pepper the region, including Trumpler 14 and Trumpler 16, collections of massive young stars that are the primary drivers of the nebula's evolution. Trumpler 14 is one of the youngest known star clusters at 500,000 years old and contains stars like the O2 supergiant, HD 93129A. O-type stars are the hottest, most massive, and most luminous of all main sequence stars. They burn with surface temperatures exceeding 30,000 Kelvin and radiate primarily in ultraviolet wavelengths. HD 93129A is one of the most luminous stars in the entire Milky Way, pumping out more than 2 million times the energy of our Sun. Stars like this live fast and die young, exhausting their nuclear fuel in just a few million years before exploding as supernovae. The interaction between these massive stars and the nebula creates a feedback loop that regulates star formation on a grand scale. Radiation from these stars carved out an expanding bubble of hot gas. The hurricane blast of stellar winds and blistering ultraviolet radiation within the cavity is now compressing the surrounding walls of cold hydrogen, triggering a second stage of new star formation. This is called triggered star formation. The first generation of stars does not simply clear away the gas. They compress it, causing new stars to form in shells around the expanding bubbles. Each generation triggers the next. But there is a limit. Eventually, the massive stars use up all the available gas, or they blow it away entirely. Every single year, stellar wind gusts blow away enough of the Carina Nebula's mass to be equivalent to the size and mass of the planet Jupiter. That is one Jupiter's worth of gas, lost annually. Over millions of years, this adds up. The nebula is slowly being dismantled by the very stars it created. In another few million years, much of the gas will be gone, dispersed into the interstellar medium. What remains will be an open cluster of stars, gradually drifting apart as the galaxy's gravity pulls them in different directions. What would it be like to be inside the Carina Nebula? Imagine standing on a planet, orbiting a young star in one of the clusters. The sky would be unlike anything visible from Earth. Instead of the faint, distant stars we see on a clear night, you would be surrounded by brilliant blue giants, blazing points of light far brighter than Venus appears from Earth. Some stars would be close enough that they would show visible disks, not mere points. The brightest would cast shadows. The nebula itself would stretch across the sky, a glowing cloud of red and orange emission, laced with dark filaments of dust. You would see the pillars, towering structures that dwarf anything in our solar system, slowly changing over years and decades as the radiation sculpts them. You would see jets erupting from forming stars, golden streaks cutting through the gas. And at night, if your planet had a night, the sky would glow faintly, lit by the nebula's emission. But this environment would be deadly. The radiation levels near massive stars, like those in Trumpler 14, would be lethal. Ultraviolet light would strip away any atmosphere a planet might have. Stellar winds would sandblast its surface. Only in the outer regions of the nebula, far from the most massive stars, could life as we know it potentially exist. And even there, the environment would be harsh, subject to periodic bursts of radiation as nearby stars flare or explode. The Carina Nebula teaches us something crucial about the universe. Star formation is not a gentle process. It is violent, chaotic, driven by extremes of temperature, pressure, and radiation. The same processes that create new stars also destroy the material around them. Creation and destruction are inseparable. Every star born in the Carina Nebula is the product of compression, collision, and cosmic forces that would obliterate anything caught in their path. And yet, from this violence comes order. Planets form around young stars. Organic molecules appear in the cooling gas. The heavy elements forged in previous generations of stars, scattered by ancient supernovae, are incorporated into new solar systems. Carbon, oxygen, nitrogen, iron. All the elements necessary for life are mixed into the protoplanetary disks around forming stars. Somewhere in the Carina Nebula, perhaps in one of the dark cores that Webb's cameras cannot penetrate, a planetary system like ours may be forming right now. Our sun and our solar system may have been born inside such a region 4.6 billion years ago. The Carina Nebula is not just a distant spectacle. It is a window into our own past, showing us the violent, chaotic process that created the sun, the earth, and everything on it. The Carina Nebula is where the future is being made. Every star born there will eventually leave, drifting out into the galaxy, taking its planets with it. Some will wander alone. Others will retain companions, orbiting each other in binary or multiple systems. And perhaps, on some distant world circling one of those stars, beings will one day look up at their sky and wonder about the glowing cloud where their sun was born. But the Carina Nebula is not the only place where stars crowd together. Across the galaxy there are regions where hundreds or thousands of stars cluster so densely that they almost touch. Places where the night sky would be bright as day, lit by countless suns. Our next wonder is one such place, a stellar metropolis unlike anything else in our galaxy, a cluster so massive and so young that it will produce more than 1,500 supernovae in the span of just a few million years. That city of giants awaits us next. There is a place in our galaxy where hundreds of stars as bright as the full moon would fill your sky if you lived there. A cluster so dense that all of its stars are located within a region less than 6 light-years across, yet it contains between 50,000 and 100,000 times the mass of the Sun. This is Westerlund 1, the most massive young star cluster in the Milky Way, and in less than 40 million years, it will be the site of more than 1,500 supernovae. It is a stellar metropolis, a city of giants packed so tightly that their fates are intertwined, and their collective end will be one of the most spectacular displays of cosmic violence our galaxy has ever seen. To understand the density of Westerlund 1, consider this. The distance from our Sun to its nearest neighbor, Proxima Centauri, is just over 4 light-years. That is typical of stellar spacing in our region of the galaxy. We live in the suburbs, where stars are spread out, where there is room to breathe. But Westerlund 1 is nothing like our neighborhood. The center of Westerlund 1 packs more than 1,000 stars within just 4 light-years. If you scaled that to a human city, it would be like cramming the entire population of New York into a space the size of Central Park. The stars are not touching, but they are close enough that their gravitational interactions constantly reshape the cluster's structure. The cluster sits roughly 12,000 light-years away in the southern constellation Ara, the Altar. From Earth it appears as a faint smudge, hidden behind thick clouds of interstellar dust that block most of its light. When Swedish astronomer Bengt Westerlund discovered it in 1961 during an infrared survey, he had no idea what he had found. The cluster remained largely unstudied for decades because of the dust. Only with the advent of infrared telescopes, which can see through the dust by detecting heat rather than visible light, did astronomers begin to appreciate what Westerlund 1 truly contains. The cluster is young. Astronomers estimate its age at 4 to 5 million years, making it an infant by cosmic standards. Our Sun is 4.6 billion years old. Westerlund 1 has existed for roughly 1,000th as long. It formed in a single massive burst of star formation, a cosmic event where hundreds of thousands of solar masses worth of gas collapsed and ignited within a relatively short span. All the stars in Westerlund 1 are siblings, born from the same giant molecular cloud at approximately the same time. But these are not ordinary stars. All stars identified in this cluster are evolved and very massive. There are no sun-like stars visible here, no red dwarfs, no white dwarfs. The cluster is dominated by giants and supergiants, stars so massive and so bright that they dwarf our Sun in every measurable way. The cluster contains 6 yellow hypergiants, 4 red supergiants, including Westerlund 126, 24 Wolf-Rayet stars, a luminous blue variable, many OB supergiants, and an unusual supergiant star. This diversity of stellar types, all present in the same cluster, makes Westerlund 1 unique in our galaxy. Yellow hypergiants are among the rarest stars in existence. They shine with a brilliance of almost 1 million suns. These stars are so luminous that they sit at the very edge of stability, their own radiation pressure threatening to blow them apart. Westerlund 1 contains 6 of them, more than are known in the rest of the Milky Way combined in one location. Then there are the red supergiants, bloated giants in the final stages of their lives. Westerlund 126, one of the 4 red supergiants in the cluster, is a candidate for the largest known star in the galaxy. If you placed one of these stars at the center of the solar system, it would almost reach the orbit of Saturn. These red giants are cool on their surfaces, only a few thousand degrees, but their sheer size makes them incredibly luminous. Wolf-Rayet stars are something else entirely. These are stars that have shed their outer hydrogen layers, exposing their helium cores. They burn with extreme intensity, their surfaces heated to over 100,000 degrees. They drive powerful stellar winds that blow material into space at thousands of kilometers per second. 24 Wolf-Rayet stars in one cluster is extraordinary. These objects are so rare that only a few hundred are known in the entire Milky Way. The cluster also contains one luminous blue variable, a type of star known for its unpredictable outbursts. Eta Carinae, which we encountered earlier, is the most famous example. Luminous blue variables are hypergiant stars that undergo periodic eruptions, shedding enormous amounts of mass in sudden, violent events. They are among the most luminous stars in the universe and are thought to be in the final stages before exploding as supernovae. What would it be like to stand on a planet within Westerlund 1? The sky would be unlike anything imaginable from Earth. Instead of the faint pinpricks of light we see on a clear night, you would be surrounded by hundreds of brilliant suns. If the solar system were located at the heart of this remarkable cluster, our sky would be full of hundreds of stars, as bright as the full moon. Stars bright enough to read by at midnight, bright enough to cast sharp shadows. Some would show visible disks, not mere points. The brightest would be blue-white giants, blazing like arc welders. Others would glow orange or red, cooler, but still intensely luminous. The combined light from these stars would heat your planet far beyond what the sun provides to Earth. Unless your world orbited very far from the cluster's core, it would be scorched by the radiation from hundreds of nearby giants. And the radiation would not be limited to visible light. The ultraviolet output from the massive stars would be intense, stripping away atmospheres, breaking apart organic molecules, sterilizing any surface exposed to the sky. But the real danger would not be the light. It would be the supernovae. Westerlund 1's stars are racing toward explosive deaths. Massive stars live fast and die young. The more massive a star, the shorter its lifespan. Stars like our sun can shine for 10 billion years, but a star 40 times the mass of the sun will exhaust its fuel in just a few million years. The cluster contains so many massive stars that in a time span of less than 40 million years, it will be the site of more than 1,500 supernovae. 1,500 supernovae. Let that sink in. Over the next 40 million years, this cluster will experience an average of one supernova every 26,000 years. For comparison, the Milky Way as a whole produces roughly 1 to 3 supernovae per century. Westerlund 1, a cluster containing less than 1/10,000th of the galaxy's mass, will produce hundreds of times more supernovae per unit mass than the rest of the galaxy combined. Each supernova will release enormous energy in seconds. The explosions will flood the cluster with radiation, shock waves, and high-energy particles. Any planets in the cluster will be subjected to repeated bursts of X-rays and gamma rays. The cluster already shows evidence of past supernovae. X-ray observations have revealed the presence of an anomalous X-ray pulsar, a slowly rotating neutron star that must have formed from a high-mass progenitor star. This is a magnetar, a type of neutron star with an extraordinarily powerful magnetic field. Magnetars are rare, and their formation requires a progenitor star of at least 40 solar masses. The presence of this magnetar tells us that Westerlund 1 has already experienced at least one supernova, and that the most massive stars in the cluster's initial population have already died. But curiously, astronomers have detected very few other supernova remnants in Westerlund 1. Theory predicts that the cluster should have experienced 50 to 150 supernovae by now, based on its age and stellar population. Yet only one definitive remnant has been found. Where are the others? This is one of the mysteries surrounding Westerlund 1. Possible explanations include that the supernova explosions ejected their remnants from the cluster at high velocities, or that many of the massive stars collapsed directly into black holes without producing visible supernovae. The answer remains unknown. The cluster's future is more certain. Over the next few million years, the Wolf-Rayet stars will explode. These are the cluster's most evolved massive stars, already in the final stages of burning their nuclear fuel. After them, the luminous blue variable will likely erupt in a hypernova, an especially energetic supernova that may produce a burst of gamma rays. Then the yellow hypergiants will go, followed by the blue supergiants, and finally the red supergiants. The explosions will reshape the cluster. Each supernova will inject enormous amounts of energy and momentum into the surrounding gas, driving shock waves that heat and compress the interstellar medium. The combined effect of hundreds of supernovae will create what astronomers call a superbubble, a vast cavity of hot, low-density gas surrounded by a shell of compressed material. This shell may eventually collapse under its own gravity, triggering a new round of star formation. The heavy elements forged in the supernova explosions, carbon, oxygen, silicon, iron, will be scattered into space, enriching the gas and altering the composition of any future stars that form from it. Westerlund 1 represents a glimpse into our galaxy's past. The Milky Way galaxy used to produce many more stars, likely hitting its peak of churning out dozens or hundreds of stars per year about 10 billion years ago. Most of that star formation occurred in massive clusters like Westerlund 1, superstar clusters that packed tens of thousands of solar masses into compact regions. Today, only a handful of these superstar clusters remain in the Milky Way. Most have either dispersed, their stars drifting apart over billions of years, or evolved into globular clusters, ancient spherical collections of stars that orbit the galaxy like satellites. Westerlund 1 will likely follow the latter path. In the future, it is believed that it will likely evolve from an open cluster into a globular cluster. As its massive stars die and their remnants either escape or settle into the cluster's core, Westerlund 1 will lose mass and gradually become more tightly bound. Billions of years from now, long after the last supernova has faded, the cluster may still exist as a dense ball of low-mass stars, a relic of this violent era. But for now, Westerlund 1 is alive with activity. It is a laboratory for studying massive star evolution, a place where the full range of stellar life cycles is on display. Astronomers study Westerlund 1 because it offers something no other cluster can provide: a diverse population of massive stars, all at the same distance, all with the same age and initial composition. This allows for direct comparisons between different types of stars and different evolutionary stages, testing theories of how massive stars live and die. The James Webb Space Telescope's recent observations of Westerlund 1 have revealed the cluster in unprecedented detail. Webb's infrared cameras can see through the dust that hides the cluster from optical telescopes, resolving individual stars and revealing structures invisible in other wavelengths. The images show not just the bright giants, but also fainter stars, lower mass objects that have remained hidden until now. These observations are helping astronomers understand not just the massive stars, but the full stellar population of the cluster, from the smallest stars to the largest. Westerlund 1 is a monument to the extremes of stellar existence. It is density, luminosity, and violence condensed into a space smaller than the distance between nearby stars in our region of the galaxy. It is a city of giants, a metropolis where every resident is a massive star racing toward an explosive end. And over the next 40 million years, we will watch as that city tears itself apart, star by star, supernova by supernova, until nothing remains but the remnants and the memory of what once was. Our next wonder takes us in a different direction, from the grandeur of massive stars to the extremes of stellar remnants. We have seen stars that are enormous in size, brilliant in luminosity, violent in their deaths. Now we turn to something stranger, a star that has already died, collapsed into an object so dense that a teaspoon of its material would weigh as much as a mountain. And this dead star spins. It spins faster than anything else in the galaxy, rotating hundreds of times every single second, pushing the limits of what physics allows. That cosmic lighthouse awaits us next. There is an object in our galaxy that spins 716 times every single second. 716 complete rotations. In the time it takes you to read this sentence, it has turned thousands of times. This is PSR J17482446 AD, a neutron star located 18,000 light-years away in the globular cluster Terzan 5, and it is the fastest spinning object known in the Milky Way. We'll just call it J1748 from this point, to shorten its long name. At its equator, matter moves at 1/4 the speed of light. Any faster, and the star would tear itself apart, flinging its material into space like a cosmic carousel, spinning out of control. To appreciate how fast this is, consider that a kitchen blender at its highest setting spins at about 250 to 500 times per second. J1748 rotates nearly 3 times faster than the fastest blender. But this is not a small appliance. This is a star, an object with more mass than the sun, compressed into a sphere just 20 kilometers across. A city-sized object spinning 700 times per second. A neutron star is what remains after a massive star explodes in a supernova. When the core of a star at least 8 times more massive than the sun runs out of nuclear fuel, it collapses catastrophically. In less than a second, the core shrinks from something the size of Earth to a sphere about as wide as Manhattan. The collapse compresses matter to densities that defy imagination. Protons and electrons are crushed together, merging into neutrons. What emerges is an object composed almost entirely of neutrons, packed together as tightly as particles in an atomic nucleus. The density of a neutron star is so extreme that 1 teaspoon of its material would have a mass over 5 trillion kilograms, about 900 times the mass of the Great Pyramid of Giza. Think about that. A teaspoon. 5 milliliters. The amount of sugar you might put in your coffee. If that teaspoon contained neutron star material instead, it would weigh more than Mount Everest. The gravitational field at the surface of a neutron star is hundreds of billions of times stronger than Earth's. If you could stand on a neutron star, which you cannot because you would be instantly crushed into a layer of atoms 1 atom thick, you would weigh roughly 100 billion times more than you do on Earth. The internal structure of a neutron star is unlike anything else in the universe. At the surface, there is a thin crust of iron nuclei arranged in a crystal lattice, similar to the structure of a metal, but far denser. Below that, as you descend deeper, the pressure increases and the nuclei become more neutron-rich. Eventually, free neutrons begin to leak out of the nuclei, creating a fluid of neutrons that coexists with the nuclear lattice. Deeper still, in a region called the inner crust, the nuclei become so deformed by pressure that they stretch into bizarre shapes. Physicists call these structures nuclear pasta because they resemble spaghetti, lasagna, and other pasta shapes. Long cylindrical rods of nuclear matter. Flat sheets. Bubbles. These structures exist nowhere else in the universe, created by the balance between nuclear forces trying to hold matter together and the immense pressure trying to squeeze it into the smallest possible space. At the very center of the neutron star lies the core, where densities reach levels that exceed even those inside atomic nuclei. What exists here is still a matter of debate. It might be a superfluid of neutrons. It might contain exotic particles like hyperons or strange quarks. Some theories suggest the core could be composed of quark matter, a state where neutrons themselves break apart into their constituent quarks, forming a quark-gluon plasma. The truth is, we do not know. Neutron star cores are the densest observable matter in the universe, and we cannot recreate these conditions in laboratories on Earth. The fastest spinning pulsar ever known began its existence as a normal neutron star, spinning perhaps 20 or 30 times per second when it first formed. Young neutron stars typically rotate this fast because of conservation of angular momentum. When the massive parent star collapsed, its rotation sped up, just as an ice skater spins faster when they pull their arms in. But 20 or 30 rotations per second is nowhere near 716. Something happened to accelerate J1748 to its current breakneck pace. The answer lies in its companion. J1748 is part of a binary system. Orbiting it every 26 hours is another star, a bloated object with only about 1/7 the mass of our Sun. This companion star is gradually being consumed. Matter from the companion flows onto the neutron star, spiraling inward through an accretion disk before crashing onto the surface. Each gram of infalling material carries angular momentum, and as the neutron star captures this matter, it gains that momentum and spins faster. This process is called recycling, and it is how neutron stars can be spun up to millisecond periods. The spin-up process takes millions of years. Slowly, gradually, the neutron star captures material and accelerates. Eventually, the accretion stops, either because the companion runs out of material or because the system's geometry changes. What remains is a millisecond pulsar, a neutron star spinning hundreds of times per second, powered not by accretion, but by the rotational energy stored in its incredibly rapid spin. And J1748 does more than just spin. It pulses. Every rotation, the neutron star emits a beam of radiation from its magnetic poles. The star has a magnetic field 1 trillion times stronger than the Sun's. This magnetic field accelerates charged particles to nearly the speed of light, creating beams of radio waves, X-rays, and gamma rays that sweep through space like lighthouse beams. Because the magnetic axis is tilted relative to the rotation axis, these beams rotate with the star, and once per rotation, they sweep past Earth. From our perspective, we see a flash of radio waves every 1.4 milliseconds, 716 flashes per second. The pulses are so regular, so precise, that millisecond pulsars are among the most accurate clocks in the universe. Over years of observation, the timing of these pulses can be measured with a precision of microseconds. This regularity makes pulsars useful for detecting gravitational waves, testing theories of gravity, and even discovering planets orbiting distant stars. J1748's location in Terzan 5 is significant. Globular clusters are ancient, spherical collections of stars that orbit the Milky Way like satellites. They are among the oldest structures in the galaxy, containing stars that formed more than 10 billion years ago. Terzan 5 is unusual, having a higher star concentration than any other cluster. The density of stars in the cluster's core is so high that interactions between stars are common. Stars pass close to each other. Binary systems form. Companions are exchanged. This dynamic environment is ideal for creating millisecond pulsars. In fact, Terzan 5 contains at least 49 confirmed millisecond pulsars, the largest population of any globular cluster known. J1748 is just one of them, though it is the fastest. The cluster is a laboratory for studying extreme stellar evolution, a place where the collision and interaction of stars create objects that could not form in the quieter regions of the galaxy. What would it be like to observe J1748 up close? From a safe distance, say a few thousand kilometers away, the neutron star would appear as a small, brilliantly glowing sphere. The surface temperature of a neutron star can exceed 1 million degrees, hot enough to emit X-rays. The star would glow with a bluish-white light, though most of its emission would be in wavelengths invisible to human eyes. But the most striking feature would be the motion. Even from thousands of kilometers away, you might be able to perceive the spin. The neutron star rotates so fast that features on its surface would blur into streaks. At the equator, matter is moving at 75,000 kilometers per second, 1/4 the speed of light. At these velocities, relativistic effects become significant. Time runs slightly slower at the equator than at the poles. The star is slightly oblate, flattened by its rotation. If it spun any faster, the centrifugal force would overcome gravity, and the star would begin shedding material from its equator. This is why J1748 represents an upper limit. Theorists calculate that pulsars could rotate as fast as 72,000 RPM before breaking apart, yet J1748 reaches nearly 43,000 RPM, about 60% of the theoretical maximum. The gap between observation and theory suggests that either pulsars cannot be spun up beyond this speed, or that faster pulsars exist, but are difficult to detect. Radio surveys may have missed them. Future observations with more sensitive telescopes might reveal even faster spinners, though J1748 will be hard to beat. The pulsar is also eclipsing. Every 26 hours, the companion passes in front of the pulsar, blocking 40% of its light. During these eclipses, which last about 10 hours, the pulsar's signal fades as the companion's extended atmosphere absorbs and scatters the radio waves. This adds a second layer of variability to the pulsar's emission. It flashes 716 times per second from its rotation, and it dims once every 26 hours from the eclipse. The combination makes J1748 variable in two distinct ways: a clockwork precision overlaid with a slower rhythm. The companion star is itself strange. It contains only about 1/7 the mass of the Sun, but has a radius of 5 to 6 solar radii, making it a bloated, low-mass giant. Researchers speculate the companion may be a bloated main sequence star, possibly still filling its Roche lobe. The Roche lobe is the region around a star in a binary system within which material is gravitationally bound to that star. If the companion is filling its Roche lobe, Material is still flowing from the companion onto the pulsar, though the accretion rate may be low. Over time, the pulsar may evaporate the companion entirely, leaving behind a solitary millisecond pulsar. J1748 will not spin forever. Gradually, over millions of years, the pulsar loses energy. The spinning magnetic field radiates electromagnetic energy into space. The pulsar slows down. This process is called spin down, and it is how we determine the ages of pulsars. By measuring how fast a pulsar is slowing, we can estimate how long it has been spinning. J1748 is slowing very gradually, which suggests it is relatively young as millisecond pulsars go, perhaps only a few 100 million years old. Eventually, the pulsar will slow to the point where its radio emission becomes too weak to detect. It will fade from view, becoming an invisible neutron star, still spinning but no longer broadcasting its presence to the universe. This is the fate of all pulsars. They are temporary beacons, shining for a cosmically brief period before falling silent. But for now, J1748 endures. Every 1.4 milliseconds, it completes another rotation. Every rotation, it sends another pulse of radio waves racing through space. Some of those pulses, after traveling for 18,000 years, reach Earth, where radio telescopes detect them and astronomers study them, marveling at the physics that allows such an object to exist. J1748 represents the extremes of density, rotation, and magnetic fields. It is a neutron star pushed to the limits of what physics allows. It is a clock more precise than any human-made timepiece. It is a laboratory for studying matter under conditions we cannot recreate on Earth, and it is a reminder that the universe contains phenomena so strange, so extreme, that they challenge our understanding of what is possible. We have journeyed through the 7 wonders of the Milky Way, from the supermassive black hole at our galaxy's heart to the fastest star circling it, from the largest known star to the doomed hypergiant awaiting its explosive end, from the stellar nursery where new stars are born to the crowded cluster where hundreds will die in supernova explosions, and finally, to the fastest spinning object in the galaxy, a neutron star rotating at the very edge of stability. These 7 wonders showcase the full range of extremes our galaxy contains. Gravity so strong it warps space-time, velocities approaching the speed of light, stars so large they dwarf our solar system, luminosities millions of times greater than our sun, densities beyond comprehension, and rotation so fast that matter itself is flung toward the cosmic speed limit. But these wonders are not isolated curiosities. They are part of a larger story, the story of how galaxies form, evolve, and change over billions of years. Every massive star that explodes enriches the interstellar medium with heavy elements. Every stellar nursery converts hydrogen into stars and planets. Every neutron star and black hole represents the end point of stellar evolution, the final resting place of matter after a life spent shining in the cosmic darkness. And we are part of this story. The atoms in our bodies were forged inside massive stars and scattered into space by supernova explosions. We are not separate from the wonders of the Milky Way. We are made of them, temporary arrangements of stellar debris that have become aware of our own cosmic origins. The Milky Way is our home, a spiral galaxy 100,000 light-years across, containing hundreds of billions of stars, orbited by smaller galaxies, rotating once every 250 million years. And at various points within this vast structure, wonders exist that push the boundaries of physics, that demonstrate the extremes of what matter and energy can do when shaped by gravity, pressure, temperature, and time. These 7 wonders are just the beginning. The galaxy contains countless other marvels waiting to be discovered. Planets orbiting distant stars, nebulae glowing in colors our eyes cannot see, binary stars locked in gravitational dances, rogue planets wandering between the stars, black holes consuming matter and warping space-time, magnetars with magnetic fields so strong they could kill you from 1,000 miles away, and perhaps, somewhere out there, other intelligences looking up at their own night skies and wondering what lies beyond. The universe is vast, ancient, and filled with wonders. The Milky Way, our galaxy, our home, contains enough mysteries to occupy humanity for centuries to come. And every time we look up at the night sky, we are looking back through time, seeing light that has traveled for years, decades, centuries, or millennia to reach our eyes. We are connected to the cosmos in ways both physical and observational, made of its matter and illuminated by its light. The 7 wonders of the Milky Way remind us of this connection. They show us what is possible, what exists, what the laws of physics allow when taken to their extremes, and they invite us to keep looking, keep exploring, keep asking questions about the universe we inhabit, because somewhere out there, beyond the reach of our current telescopes, beyond the limits of our present understanding, other wonders await. The journey has only just begun.